Last time, we figured out how the ECG sees the heart. 10 electrodes, 12 leads, 12 different angles, all watching the same heartbeat at the same time. And each lead doing one thing, deciding whether the electrical wave is coming towards it or moving away from it. Towards the positive pole, deflection goes up. Away from the positive pole, deflection goes down. That gave us the first thing we needed, direction of the wave. But direction alone isn't enough. Knowing a wave went up doesn't tell you much. How high did it go? How long did it last? To read an ECG, you need three things from every electrical wave: direction, voltage, and time. The leads gave us direction. The ECG paper gives us the other two. And that's what this lecture is about. When you look at an ECG strip for the first time, it looks complicated. Waves going up and down, lines everywhere. But underneath all of that is just a grid. A very deliberate, precise grid. With two sizes of squares. Large squares, which are 5 millimeters on each side, and small squares, which are 1 millimeter on each side. Each large square is made up of 5 small squares in each direction. Every square on that grid means something, and what it means depends on which direction you are reading. Let's first read the paper horizontally. The ECG paper doesn't sit still inside the ECG machine. It moves. It rolls under the stylus at a fixed speed. The standard speed is 25 millimeters per second, which means that every millimeter of paper that passes represents a fixed amount of time. So, one large square equals 0.2 seconds. And one small square equals 0.04 seconds. And this is only measured horizontally. If you want to add more, 5 large squares give us 1 full second. So when you look at a wave and measure how wide it is, you are measuring time. How long that electrical event took to travel. A wide wave means slow conduction. The electricity moved slowly through the tissue. A narrow wave means fast conduction. Electricity moved faster through the tissue. Therefore, width is about the speed of conduction. Now let's read the other direction, vertically. The stylus moves up and down based on the voltage the electrode detects, and the paper records exactly how far it moved. The calibration is simple. One large square vertically equals 0.5 millivolts, and one small square vertically equals 0.1 millivolts. So when you look at how tall a wave is, you are measuring voltage. How much electrical force reached that electrode. A tall wave means more voltage reached the electrode. A short wave means less voltage reached the electrode. Simple so far, but there's an important thing to note for. The natural assumption is bigger wave equal bigger heart event. Taller peak equals more cells firing or more heart is involved. But that's not what voltage measures. Voltage at the electrode depends on three things. how much electricity the heart actually generated, the direction that electricity is moving relative to this lead, and the distance between the heart and the electrode. Fat, fluid, and air in lungs, all of these sit between the heart and the skin. All of them reduce the signal. So, a small wave might mean weak electricity, or it might just mean the signal had a long way to travel. And a tall wave might mean strong electricity, or the electrode just happens to be perfectly aligned with the direction of that wave. Amplitude reflects electrical force at that angle, at that distance, not heart size. Hold on to that, it will matter later. One more thing before we move on, and this one is practical. 25 millimeters per second is the standard speed, but some machines run at 50, which is double the speed. This can be used when the heart rate is very fast, and the complexes are crowding together, making them harder to read. Stretching them out makes the details visible. So let's close the loop. The heart generates electricity. The leads capture it and determine direction, toward or away from the positive pole. And the paper draws it, converting that signal into something you can see, measure, and read. Horizontally, time; vertically, voltage. 3 components: direction, voltage, and time. Now you have all 3. The ECG paper is not a mystery, it's a grid. And now you can read it. But here's the thing. We've been talking about the paper, the recording. We haven't yet talked about who's watching from where, which lead is sitting where on the body, what angle each one is looking from, and why that matters for everything you'll read. That's next. That's all. Thank you and see you in the next video.